Hey guys, today we're going to learn how to find the acceleration of a mass down a frictionless inclined plane. And the first thing we got to do, like any problem, is to label a free body diagram. Alright, so on this free body diagram we're going to draw the center of the mass here, and the first thing we always have that's always straight down is the force of gravity. That's the force of gravity, which is always equal to mg. Right? The next force we need to include on it is, well, we have to have this plane exerting a force up on this to keep it in equilibrium. So, well, currently equilibrium. It will slide eventually, but it's not going to jump off the plane or jump into the plane, so there has to be a normal force. Force normal. Alright, and this normal force is not straight up like we typically draw when on a flat table. You gotta remember, it is perpendicular to the plane. Alright, so let's look at this, and we need to next determine what's the net force. Now this is our free body diagram. There's no other forces here. If there was friction, then we'd add friction in, but we'll talk about that soon. Well, what's the net force? Well, we have a normal force up, but a force of gravity down. But if we think about this, this block is going to tend to have an acceleration to the left. It's going to have an acceleration to the left. It's going to want to slide down the plane. So we're going to have a net force in this direction. So how do we find that? Well, we see that this ramp is at some angle theta, and for what it's worth, we'll call angle theta 30 degrees. I know it's probably not, it looks a little shorter than that, but we'll call it that for now. Well, what we have here is we have to kind of tilt our head a little bit. And if we know that this is going to be our object sliding down the plane, then if we realign it so that the surface it's sliding on is now thought of as our x-axis, and the surface, the line perpendicular to that, is thought of as our y-axis, then we have an easy way to go about solving this. Okay? We can now say that, well, we have this force of gravity pulling down at some angle to the y-axis. And knowing that these are similar triangles, we can use math to show you that later, but that means that this angle right here is actually 30 degrees as well. Well, if we know the angle, and we know we have force of gravity pulling straight down, we really just have some type of component system. We now know that if it's pulling down an angle to the x and the y, there's going to be some force of gravity in the y direction, and it's going to be some force of gravity. But let me undo that. Alright, and there's going to be some force of gravity in the x direction. So this is our force of gravity y. This is our force of gravity x. Now what are those values? Well, it's easy if we see this is the angle, force of gravity is the hypotenuse, and this is the adjacent to that. That means force of gravity in the y direction is just the force of gravity cosine theta. And force of gravity x equal to force of gravity sine theta. Right. Well, let's see here. If I'm going to drop down here, I'm going to say that down below, if we look in our y direction, you can see that the sum of the forces must be equal to 0, because this mass is not going to accelerate off the plane. It's not going to accelerate into the plane. it's going to slide in the x direction. So the sum of forces in the y direction is 0, which must mean that the forces up, force normal, and the forces down, which is the force of gravity in the y direction, must be equal. So what does that mean? That means the force normal is actually less than what it would be if this was a flat plane. While in the x direction, there's going to be an acceleration. So that means the net force in the x direction is going to be equal to the mass times the acceleration in that x direction. But there's only one force here that could possibly cause it to accelerate, and that is the force of gravity in the x direction. That's the only x force we have. So the sum of all the force in the x direction would be the force gravity x, which equals ma in the x direction. Well, we know the force gravity in x is Fg sine theta, but don't forget Fg is just equal to mg, so I'm going to rewrite this as mg sine theta is equal to max. Well, life gets a little bit easier here if we notice that on both of these there is an m, and that's the mass of the object. And this is super, super important because this means that mass doesn't affect the acceleration. Affect A. Okay. Acceleration is just going to be g sine theta is always going to be equal to acceleration in the x direction or down the plane. So knowing that mass does not affect the acceleration down the plane, the only two things that affect the acceleration is the gravity that's exerted on it and the angle at which the plane is set at. So that doesn't mean if you have an elephant on here or if you have a chipmunk on here. If it was frictionless, it would slide down at exactly the same acceleration. All right. And then if you want to know anything about that, well, we know that the object would start from rest, where v initial is 0, and it would pick up speed. So really all we have then is we have to use the kinematic equations to find anything else. So we have calculated acceleration, we have determined the net force. The net force would be in the x direction. It is based off force gravity x. We have labeled it. This completes how to find an acceleration with a frictionless plane. Now they're going to toss in other questions to you here as well. Like maybe they'll say, okay, what if there's a wall up at the top of here, and on that wall there is a string that ties to the box, keeping the box at rest. What is the tension in the string? Find tension. Alright, and this is a totally fine problem, and you know how to do it, because you know that if this box is at rest, then it has no acceleration in the y direction or the x direction, so that tension must be a canceling force out with the other x direction force, because this tension would be to the right on the x direction, and it would have to cancel out with the force of gravity x in the x direction to the left. So this tension must be equal to the, let me erase this, oh no, I erased everything. So that means that the tension would be equal to the force of gravity in the x direction. So hopefully that was helpful. I want you to try a couple problems I'll give home with you. Take care and enjoy. Now take a look at a series of masses that are resting on inclined planes, but that all of which have different angles. And imagine that underneath each of these there was a scale, some scale that rested underneath these masses. Would the scale measure the mass's weight the same or different in each of these following scenarios? Now remember, when you're standing up on a scale, the scale measures your weight, but really what it's measuring is your apparent weight. And we know that it's apparent weight because it can appear to change. If you get an elevator on a scale, you know that as it goes up and as it goes down, or accelerates up and accelerates down, I should say, the apparent weight is going to change. Well, let's take a look at these scenarios. If we redraw our free body diagram, we still have the force of gravity straight down. That's F sub g, also known as weight. And that's the real weight of it. Alright, following that, we also have the normal force perpendicular to the plane, so that's going to go off at some degree here. So what is this normal force? Well, we know that without friction, this block is going to slide down in the x direction. It's going to accelerate to the left. In all these cases, we're going to have acceleration down the ramp. Just like this. Okay. So, that means that the block will not have acceleration up nor down, which means that the force normal has to cancel out with the y component, force gravity y, because we know the acceleration, as we learned before, is going to be based off the force gravity x. And if we remember that the force gravity y in all of these is going to be equal to mg sine, cosine, let me do that cosine theta, because the angle that this is at right here, this theta, is the same as the angle right here, theta. So ft is adjacent to that. So that means what happens to, we know that m and g are not going to change in any of these scenarios, but what happens to cosine as theta gets larger? I mean, this theta is going to increase from, well, the smallest theta is down here to the largest theta right here. So what happens as theta approaches 90 degrees, which is perfectly vertical? Well, as cosine of theta goes to 90 degrees, cosine theta goes to 0. Meaning that as the angle gets larger, meaning the theta is going to 90 degrees, the cosine is going to 0, which means that the force gravity in the y direction, so I have to put y there, is going to go down. Meaning that as the angle gets steeper, the force normal is actually decreasing because the force of gravity in the y direction is decreasing. Okay. So, sorry, mess up there. As theta increases, the force normal must decrease. I'm just going to draw arrow down, must go down. Alright, that means that apparent weight is going down because apparent weight is always based off force normal. But it also means that as theta goes up, the acceleration is going to increase because we're losing more. Let's get a different color here. We're losing more of the y component, but we're gaining more of the x component. Force gravity x is going up, and force gravity in the y direction is going down. Right? So we can conclude that as the angle of the inclined plane is increasing, the normal force will decrease. And we can think about that on the two extremes. The first extreme, when is a mass on flat ground? If it's on flat ground, the force of gravity must be equal to the force normal. But if that angle was perfectly vertical, imagine a vertical wall here, and you put a mass here on that wall. Guess what? That mass is going to fall down with an acceleration equal to g.